Welcome. This video is going to take a look at pH scale. How is it devised and what exactly do the numbers mean? So it's a quantitative scale based on the hydrogen ion concentration in an aqueous solution. And since the majority of acids are weak, that means not much of the acid or the hydrogen actually falls off. If we expressed H plus as its actual concentration in moles per liter, it would give us numbers with large negative exponents. And since that's kind of cumbersome to work with, in 1909, Sorensen came up with the idea that pH instead be the negative log of the hydrogen ion concentration, or in other words, the exponent with the sign flipped. That means that if you know the H plus ion concentration, or if you know the pH, you can get the H plus ion concentration by taking 10 to the minus pH. So we can go either direction with this idea. pH is usually positive and it's expressed with no units. So let's take a quick look at how you would use this. If I knew the hydrogen ion concentration of blood to be 4.6 times 10 to the minus 8 moles per liter, I could go ahead and find the negative log of this concentration, and I'd know the pH is 7.33. If, on the other hand, I told you the pH of blood is 7.33, and I said, what could you expect the hydrogen ion concentration to be? Then I would take 10 to the negative 7.33 to come up with my ion concentration of 4.6 times 10 to the minus 8th. Now the sig figs are a little bit weird because you maybe noticed that I only had 2 sig figs with the 4.6, but I carried 3 sig figs in my answers. That's because it's a logarithm, and the convention is that you get to keep the number of decimals equal to the number of sig figs in your original number. And that's a good thing because a small change in pH is actually tenfold. A 1 unit change is tenfold. So if we round it to whole numbers, we could actually be rounding tens at a time. We're talking about a big change in pH. So this is more precise. Works out. How about if you're actually measuring pH in the lab? Well, the simplest way is to use universal indicator, and it can be paper or solution. It's quick and cheap. You just dip it in or you add it to your solution and see what color it is. But you have to compare the color to a chart. So it all depends on, how well you interpret the color. What you might interpret as being an 8, somebody else might interpret as a 9 or a 7. You can also use a broader range or narrower range indicator. A broad range would just be the blue and red litmus to know if it's acid or base. Or you can use things with a far narrower range that maybe get you down to half a pH unit. But if you want to be really precise, a pH meter is the way to go because it uses an electrode to actually measure the conductivity and determine the pH. But it's going to be more expensive and it's going to be putzier to do because you have to calibrate the pH meter with buffers and you need to standardize it for the temperature. So the question is, how much time do you want to spend and how precise does your measurement need to be? So where did the 0 and 14 and 7 all come from? Well, it's based off this idea that water also ionizes. Acids and bases are defined by the H plus or the OH minus that they release in an aqueous solution. But remember, water contains both these ions, and water actually dissociates or breaks apart slightly in any sample. If you're drinking a glass of just water, there is some H2O molecules, and there are also some H plus and OH minus ions in there. But we don't notice it because it doesn't behave any different. This idea is known as the self-ionization of water, and where it's pure water, your H plus concentration and your OH minus concentration should be equal. And so since it's a reversible reaction and the equilibrium lies very far to the left, we should be able to find an equilibrium constant for this, and we call this the Kw. And Kw would be equal to your hydrogen ion times your hydroxide ion concentration divided by water's concentration. But water's concentration is just going to be 1. Since it's a liquid, it would be its density. So it's really just H plus times OH minus concentrations. And what scientists have come up with is this value is 10 to the minus 14th. If you take it a step further then, your H plus and OH have to be equal to each other when it's water. So that means I can find the value for each of those. Dividing that by 2 means that H plus and OH minus for water are each equal to 1 times 10 to the minus 7th. Now maybe you're getting a sense of where the number is coming from on the pH scale. So H plus and OH have an inverse relationship since this constant has to hold true. So if I increase my H, as I look at my equation here, if I increase H, OH would have to decrease, and I see that. If H increases from 10 to the minus 7th to, say, 10 to the minus 6th, then OH decreases to 10 to the minus 8th. If H plus decreases to 10 to the minus 10th, then OH increases to 10 to the minus 4th. So there's a very linear inverse relationship here. That means I could have a pH as low as 0, meaning I've got virtually all H plus in there and no OH minus. 10 to the minus 14th would be a very small amount. 10 to the 0 means practically 1 or all of it. And at the other extreme, I could have virtually no H plus and all OH minus. So that's where these extremes come up. 10 to the 7th neutral is when the H plus and OH are both at 10 to the minus 7th. pH of 0 is when it's virtually all H plus. pH of 14 is when it's virtually all OH minus or no H plus. So how do we use this to manipulate pH problems? Well, if the pH of a substance changes from 3 to 5, what is the change in magnitude of H plus? And what you need to remember here is that you've changed from pH unit 3 to 4 to 5, so you've changed 2 units, but each unit is a 10-fold change, so this is really 10 to the second, or 100 times less in this case, because pH is getting higher. I've decreased my delta H plus by 100 times, or 100-fold. In my second problem, I've got my sample of blood again at 298, still has an H plus of 4.60 times 10 to the minus 8, but now I want to know what is the OH minus concentration. Well, since I know that H plus times OH minus is equal to a constant of 1.0 times 10 to the minus 14th, I can plug in the 4.60 times 10 to the minus 8th for my H plus. I guess I don't need the bracket on that because that is the concentration, times the OH minus, and this should be equal to 1 times 10 to the minus 14th. So if I move this to the other side, leaving just my OH minus, I can plug and chug here and find that my OH minus concentration is equal to 2.17 times 10 to the minus 7th, and my label would be moles per decimeter cubed because concentration does have a label. And a quick way to double check your solution here is if I take my OH minus concentration times my H plus concentration, if I multiply these two, I should get 1 times 10 to the minus 14th back, which I do. Final example is if I give you the pH of 3.28 and ask for the H plus and OH minus, this is only slightly more involved. To get my H plus, I'm going to start by taking 10 to the minus 3.28, and I get a concentration of 5.25 times 10 to the minus 4, and that's moles per decimeter cubed. And now I go ahead and set that equal to 5.25 times 10 to the minus 4 times my OH should be equal to 1 times 10 to the minus 14th. And when I solve for the OH minus, I get a concentration of 1.90 times 10 to the minus 11th. Another quick check here is if you look at your exponents, they should add up to around 13, 14, or 15, depending upon what the value is here. This would give me a minus 15, so it appears I'm in the ballpark here. And by the way, on the previous question, they had also asked if blood is acidic or basic, and you should have come up with blood being slightly acidic.